The Snake River Plain is located in southern Idaho. The basic shape of it is in a curve-shaped depression. As a whole, the Snake River Plain runs about 400 miles from west to east. The Snake River Plain is divided into two separate entities, the Western Snake River Plain and the Eastern Snake River Plain.
As shown on the Digital Atlas of Idaho website, several hypotheses exist to explain the origin of the Snake River Plain. The first hypothesis is that it was extended to the north coupled with crustal thinning. The second hypothesis is that there was migration of the continent or the North American plate over a stationary hotspot, which now exists at Yellowstone National Park. The hotspot has northeastward migration of silicic volcanic centers moving at the rate of 1 to 2 inches per year. Uplift is associated with volcanism, and silicic volcanism is followed by basaltic volcanism. The lower crust is thickened and made more dense by injection of basaltic magma. After passing over the hotspot, the crust settles due to the contraction from cooling and the density of the basalt. This hypothesis is favored. The third hypothesis is that the plain formed due to propagation of crustal fracture from west to east. The last hypothesis is that the plain formed due to passive deformation. Running 30 to 43 miles wide, the primary rock type in the western Snake River Plain is basalt, rhyolitic tuff, and ash flow. Basalt is made up of extrusive igneous rocks which form from the rapid cooling of a basaltic lava exposed at the surface of the earth. Tuff is also an igneous rock, which is formed from the blast products of a volcanic eruption. When these blast products are cemented into rock, tuff is formed.
Using the rocks found in this geographic structure as a way to find the age of the rocks, it is believed that they are about 15 to 16 million years old. This age is one that dates back to the Middle Miocene era. The structural features of the Western Plain include a very thick lower crust underneath the plain. This crust is over 25 miles thick. Contrasting from this, the upper crust, which is above the plain, is very thin. The plain is bounded by normal faults. Normal faults occur when the lithosphere is being extended. The land surface and rock layers of the Western Plain slant towards the middle of the plain, creating a dip in the geographic structure.
Due to its characteristics, the Western Plain is thought by some scholars to be a graben. A graben is a block that is dropped relatively downward between two normal faults, dipping towards each other. However, there are some scholars that do not agree that this is a geologic structure that should be defined as a graben. This plain is also one that is defined by multiple past basaltic volcanoes. While researching the Snake River Plains, we realized what a large area it really is, and as a result, thought there would be a lot of natural resources found. This wasn't the case. In fact, the only natural resources we could find as we researched the Western Plain were deep wells that are drilled into the earth which produce water. As the wells were dug deeper, another resource was found. This other resource was a deposit of granite. The primary rock types found in the eastern Snake River Plain are basaltic and silicic volcanic rocks that have very little sediments. We already mentioned earlier how basaltic rocks are formed. Silicic rocks are quite similar. Like a basaltic rock, it is an igneous rock and has a volcanic origin. However, As the name suggests, silicic rock has a very high amount of silica. In order to qualify as a silicic rock, this rock must contain 65% or more of silica. In the Eastern Plain, the rocks range from an age of 6.2 to 10 million years old. The last big eruption of silicic volcanics is represented by the Yellowstone tuffs, which are about 600,000 to 2 million years old. Fairly recently, at about 700,000 years ago, rhyolite flows erupted. In addition, rhyolite domes near the axis of the plain date to 300,000 to 1.5 million years ago.
The eastern Snake River Plain is made up of higher land surface around the edges, a lot like the western plain, and then it dips in at the center. This dip is due to the weight of the overlaying volcanic rock. However, as you progress to the eastern side of the East Plain, the upper crust thickens. To the north and south of the plain lies the Basin and Range provinces. Gravity anomalies in this plain are a lot higher than the areas around it. These anomalies have random highs and lows with no linear anomalies aligned with the axis of the plain. Throughout the eastern plain, there are many extinct volcano centers. Located near these centers are 5 rhyolite domes. These names of these domes are the Cedar, the Middle, the Big Southern, the Unnamed, and the East Buttes. Domes form when viscous magma erupts effusively onto the surface and then flows around this eruption, forming a raised dome shape.
The typical accepted model for the Eastern Plain is called the hotspot origin model. This model shows that the Snake River Plains formed from the North American plate moving over a stationary mantle plume. This plume is located beneath Yellowstone National Park. The plate moves at a rate of 4.5 millimeters per year. The Eastern Plains geologic history is one defined by lots of volcanic activity. However, unlike the Western Plain, there are no evidence of faults.
Making up the majority of the Snake River Plain area, the Eastern Plain has several natural resources. One of the main ones is an aquifer, which is primarily considered to be an unconfined aquifer, and lays beneath the plain. An aquifer is a water-bearing stratum of permeable rock, sand, or gravel. This eastern aquifer covers an area of approximately 28,000 square kilometers. It is held in between layers of basaltic rock, and occasionally sediments are deposited in these layers. The total thickness of the basalts in this area is around 1,500 meters. In the upper 500 meters of this aquifer alone, about 200 to 300 million acre-feet of groundwater can be stored. This aquifer drains into the Snake River and for the most part flows southwest. To obtain this groundwater, large wells are drilled into the earth. Another resource that was found in these drill holes and at the margins of the plain was rhyolite, along with an abundance of sediment.
We found the process of learning about this geologic structure to be both interesting and applicable. Being Idaho residents, it's been a unique opportunity to become more informed about the history and geology of the state we live in. Thank you for watching our video presentation on the Snake River Plain. We hope you enjoyed learning about the Snake River Plain as much as we did.